Where do we have it? Right here. Here's, do you need a calculator or you have one? Got one? All right. I'm just so used to having these classes of 48 to 72 students. It's I've never done the hybrid, so it's kind of bizarre to see this. I'm hoping it's a statement of the students' confidence rather than my incompetence in teaching.
How many students we have in total in our class?
15 are on the roster. Maybe 14 now. But there were 24 students on Tuesday of that first week. And when I met you guys the first Friday, now you were gone the first Friday, weren't you?
Yeah.
Yeah. So when we came here the first Friday, there were 9 people here, but there were 15 still on the or 16 on the roster. I went into the online office hours, which I have right after class, and there's one person waiting there, and it's like, oh, so what are we going to do today? I said, well, what we did is we met at 8 o'clock today, and for what? I said, well, for lecture. And the person replies, oh, were we supposed to be there? I said, well, it's should be on your schedule. And then left the chat room, and then 2 hours later, the student showed up on the drop list on there. So when we lost 9 people, you know, right away, they read the syllabus or whatever and decided they weren't going to be a part of this. But anyhow, well, we'll see now how well the 2 of you that entered in your answer here did. Well, one of you got it right, one of you didn't. Do you know which one of you got it right, which one of you didn't? All right. Yep. Do you want to review it? You know what you did wrong? Okay. Oh, see, did you check the answer here before you put yours in? Maybe. All right. Okay, so here's what's going to happen today, and I don't know. Hey, wow, we got 4. How about that? So if 2 is company and 3 is a crowd, 4 is bigger crowd. All right. Okay. So we're cool. Okay, so here's what we're going to do today. We're going to move on into chapter 8, and chapter 8 is on stoichiometry. Just a quick mention, your exams have been graded. The answer key was auto-posted. That went up at 1 a.m. I went through this morning, I got in early, and I went through the manual grading, so there were the few manual graded problems that went through. Everybody that's a part of this group, I guess, I can't remember if we all did as well as maybe we would have liked, but I know generally the ones that show up here regularly are the ones that do much better than those that do not show up regularly in here. So with that said, we're going to jump into chapter 8, which is on stoichiometry. Stoichiometry is a look at the mass relationships in chemical reactions. And it's a place where we kind of look at the practical application of the mole concept. And we take it from the perspective very similar to where we would, say, in an industrial or workplace setting. Example I'm giving here shows like if we were in a car factory, we would need frames, bumpers, and wheels. And in that type of scenario, we might say, well, this is how much raw materials we have. This is how many frames, bumpers, and wheels we have. We might like to know how many cars we can make out of those. Or we might look at the scenario, this is the number of cars you want to make, and we want to know how many frames, bumpers, and wheels do we need. So we can go one of those 2 ways. If you work for Subway, for example, if you know you need to make 50 sandwiches an hour, then you might want to know, well, how many slices of cheese do you need an hour? How many slices of meat do you have an hour? Whatever else. So again, you have a situation where you know what you need at the end, so you want to know how much raw materials you need. Or you might take it from the perspective, this is the amount of raw materials, we'd like to know how much product we can make. So we're going to start with this example right here. I've put a number of these into the Socrative app today. Let's say that this is an example of a chemical reaction, and we have the number of frames, bumpers, and wheels. And so what we'd like to know then is how many cars could we make if we have 50 frames, 80 bumpers, and 100 wheels. Now you can always feel free to consult one of your three neighbors in here. Didn't get the other two answers locked in here. That way, not any one person is on the spot. All right, let's check it out here. Wonderful. You guys, we can go home for the day. So if we were to look at this though, say from a way we would do this using dimensional analysis, I'm sure that many of you just kind of did this in your head. If we were to do this doing dimensional analysis, here's how this would look. We could say if we have 50 frames, we'd like to know how many cars can we make. If we have 80 bumpers, how many cars could we make? And there's a reason why I'm using the dimensional analysis here. You'll see it in a bit once we start working with less familiar units. Like how many cars we could make. So what you probably did without doing dimensional analysis is you arrived at your answers in a little bit different fashion, but here's how it would look like using dimensional analysis. According to this equation, one frame produces one car, so we would say that one frame makes one car, canceling it out like this. We could say that two bumpers makes one car like this, enables us to cancel them out like here. And we could then put in 4 wheels for every one car. And again, that's simply by looking at the relationships here in this equation. Wheels cancel out. And if we did all the math, we wind up with 50, 40, and 25. Okay, so this is how we set it up using dimensional analysis. But now all of us answered 25, and why did we answer 25? What happens? Yeah, but why couldn't we make 40? Don't have enough wheels, exactly. So that's going to be the same thing if we look at it in terms of a chemical reaction. We do give a name for it, and I don't know if how many have had some chemistry before, but we actually do give a name to these things. This one here is called the limiting reactant, at least if this was a chemical. And this one out here is called the theoretical yield. And we say that the limiting reactant is the reactant that limits the amount of product that can be produced. So again, the limiting reactant is the reactant that limits the amount of product that may be produced. And the theoretical yield we define as being the maximum amount of product we can make when all of the limiting reactant is converted into product. So again, the theoretical yield is the maximum amount of product we can make when all of the limiting reactant is turned into the product. So typically, when we're going to go through these calculations, we'll be doing the limiting reactant types in the second hour today. But typically what you're going to do then is you're going to look at all the answers presented to you, and you're going to wind up picking the answer of the 2 or 3 or whatever, that is the smallest of those 3 answers, as you mentioned already. Because this is the most we can make. That's the most we can make once we run out of the limiting reactant. So with that said, any questions that you have? All right. These up here, we refer to as the excess reactants. These here are your excess reactants, which just means that we have some of them left over at the very end. So now we might have another question that works something like this. Let's take into account what we just learned here and then go to the Socrative app. And following up on the previous problem, if 23 cars, so now we're saying if we made 23 cars out of the 50 frames, 80 bumpers, and 100 wheels, what is the percentage yield of cars? So let's think about how percentages work. Whether we're in chemistry or not, percentages are always found by taking the part and dividing it by the whole, multiplying by 100. So think what that would mean for this problem. Okay, got everyone locked in here? Okay, we'll count down here, 5, 4, 3, 2, 1. Correct answer here is a 92% yield. And of course, we get 92% how? 23 divided by 25, exactly. 23 is what we actually made. 25 is what we could have made. We take that result and multiply by 100. So our formula for percentages looks like this: part over the whole times 100. If this was a chemical reaction we're looking at, we call this percentage yield. We say it's found by taking the actual yield, the amount that we actually make, we divide it by the theoretical yield, and we take that result and multiply by 100. And if we went back to our example here with the 23 cars, what could cause us to make 23 cars instead of 25 cars? What's something that could make us, allow us to make less than 25? Well, what was our limiting reactant? The wheels. So what might be true about those wheels if we wound up with less than 25 cars? Well, yeah, but we have 100 wheels. We're told here that there's 100. So why might we wind up less than 100? Or less than 25, sorry. Well, if you buy a product, is a product always perfect? No. So we might wind up having some defective wheels in there. If we have some defective wheels, then we could wind up producing less than the 25 cars. Now in a chemical, or if you're in a Subway, for example, and you're making sandwiches, maybe you have some spoiled meat. So you have a whole bunch of meat. If something that spoils, you're going to make less than what you thought you could make at the very beginning. If you're in a chemical reaction, it's maybe not so much the chemicals would spoil, though some of them do. We wouldn't say actually they spoil, but some chemicals aren't stable and they change their composition. And the other thing is we've often assumed that the reactions that we've looked at are ideal. It is pretty much the way we write them is the way that we see them as products, but that's not always true. Many times reactions will have some byproducts or some side products, things that don't show up. For example, when you burn gasoline, one of the examples we looked at last week is that methane, we did look at methane, but gasoline is octane, and when octane reacts with oxygen, we said that the products are carbon dioxide and water. But in reality, some other products are, if you ever sat behind the exhaust of a car, you know that something else comes out other than carbon dioxide and water. You might be smelling some other, you might even be smelling gasoline. Some of it goes through unburned, or some gets converted into carbon monoxide. And so there are actually other products that wind up forming. And so it's not 100% of whatever the reaction is that we're writing. So in real reactions can have either byproducts or side products that may not show up in a chemical reaction. Very often the yield is less than 100%. And so it can never be more than 100%. If you're winding up with more than 100%, either you're making some mistake in your calculations, or if it's an actual process, that means that you're getting some other crap in there that you don't want to be in that particular reaction. And you need to wind up doing things over. Now, some other things that might happen, let's see if we look at this particular one. One of the things that often among students is wording of problems. So now if we worded it like this, we have the chemical reaction, or what is kind of a framework of a chemical reaction. We now say we have 100 wheels, but now we're not specifying the amount of frames or bumpers, we're just saying there's an excess. How many cars do you think we could make if we had 100 wheels, but there were an excess of frames and bumpers? All right, let's get our answers locked in, please. Count down, 5, 4, 3, 2, 1. All right, and of course it'll still be 25. So in this case, you may remember that when we went back and looked at our example back here, we said that these were the excess reactants. So many times when you're reading through the problems, if it refers to being excess, some reactants being present in excess, all that really means is we can ignore that in your problem. All we really need to pay attention to is the amount of the other reactant here that is given. So with that said, we're going to look at some actual chemical reactions now and work with these. And we'll start with this one right here. Let's write out a chemical equation that shows the reaction of nitrogen gas and hydrogen gas to make ammonia in the gaseous phase. So nitrogen gas reacts with hydrogen gas to produce ammonia in the gaseous phase. So let's start with the formula for nitrogen. Nitrogen gas would be N2. Hydrogen gas would be H2. And then we're producing ammonia. This is one of our to learn ones or to memorize ones from last week. Ammonia is NH3. Ammonia is NH3. The ammonium ion is NH4 with a positive charge. But this is ammonia with an IA ending, ammonia. And we'll produce it as a gas. So then at this point, we should go ahead and balance the chemical reaction. To balance this equation, we have 2 nitrogens here, only 1 here. So in front of the ammonia, we need what number? 2. And now that we put the 2 in front of the ammonia, in front of the hydrogen over here, we need to put a 3. We have our balanced chemical equation. Now, when we look at this chemical equation, we could have an interpretation that goes something like this. We could say that 1 molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. If we started with a dozen nitrogen molecules, we'd say that a dozen nitrogen molecules would react with 3 dozen hydrogen molecules to produce 2 dozen molecules of ammonia. And of course, if we multiplied by Avogadro's number, we'd say that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. And that's the way chemists wind up working with it. And we refer to that as being the molar interpretation of the chemical equation. And in the molar interpretation, each of the coefficients stand for the number of moles. So when we look at a chemical equation, we could then say that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. And if, for example, we wanted a relationship between these two here, we could then say something like this. We could say that according to this equation, 1 mole of nitrogen is equivalent to 2 moles of ammonia. Where this symbol right here stands for is equivalent to. Now sometimes we wind up writing it something like this. We could simply write it with a colon in there. And what this represents is what we call a molar ratio. And as far as what we're going to learn today, this is probably the only new conversion that we're learning today is the molar ratio, the entire 2 hours. This is really about the only thing we'll be learning. But what will happen is now we're going to use that molar ratio to kind of help us work with the mass pieces here in just a bit. But now with this, we could start off something like this. We could say, how many moles of NH3 would be needed to produce, and let's do something like this. Let's say 0.164 moles, not produce. We say, how many moles of NH3 would be made from, sorry about that. And then we'll say made from 0.164 moles of N2. We'll slide that over here. There we go. So now if we want to do this one, the math on this one is quite simple. We start off with what we're given. In this case, we're given the 0.164 moles of N2. We're trying to find, in this case, moles of NH3. If we want to do this, we then need to put in a conversion factor. The conversion that we're going to put in here, we want the units to cancel, so what are we going to put on the bottom here? It goes on the bottom. 1 mole of N2, and what's going to go on the top? And how many moles of NH3? It would be 2, exactly. So what we're going to do then is we use this molar ratio as a conversion factor, just like we did back here when we were working with the cars, where these coefficients stood for the number of moles. Again, where these coefficients stand for the number of moles, we use it as a conversion factor. At this point, the units cancel out. We take the 0.164 and multiply it by 2. And upon doing so, we wind up with an answer of 328 moles of NH3. So this is one of the ways then that we could wind up using our molar ratio. Let's go ahead and try this out on the next two here. Now we look at this chemical equation. We'd like a molar ratio between N2 and H2. Remember that the 3 lines there means is equivalent to. What is the molar ratio between N2 and H2? Look at the choices. I'll give you about 15 seconds here, unless the last person is going to ring in. All right. Very good. So let's go ahead and do this next one then. We'd like to know how many moles of N2 will react with 9.33 moles of H2. Use the molar ratio that you just came up with and calculate the moles of N2 that will react with 9.33 moles of H2. And for answer, just put in moles, M-O-L. Okay. Everybody set here? All right. We'll check them out. All right, we have one rebel here. So we need to make sure that we have this set up right. Let's look at the setup, how we did this. And there, we got the equation in mind. So we started with 9.33 moles of H2. We were looking for moles of N2. What's going to go on the bottom? 3 moles of H2. What's going to go on the top? 1 mole of N2. Now, one of the things you're going to notice here, it's going to feel very cumbersome to be writing out all of these units like this. But as we start getting into the next problems, you're going to see where writing out complete units are going to help. We take the 9.33 here, we divide it by 3, we wind up with an answer of 3.11 moles of N2. Now, of course, if we went into the lab, and you're not working in the lab here, your lab is at home in this course, we're not going to be working with moles. We won't be measuring out moles. What will we be measuring things out in? Which units? In fact, your lab, I think, is coming up for Monday. We'll be using this. So your balances don't measure in moles. They measure in what units? Grams, right. So this here would only be applicable if we're counting atoms. And so you don't have them, because the atoms are so small, you can't go home and count them. So the way that we count them is actually by weighing them. So we wind up using a balance to weigh these out. So let's go ahead then and look at how we would do this in units of grams. So we'll go back and we'll write out the same chemical equation. Nitrogen gas reacts with hydrogen gas to produce ammonia in the gaseous phase. And of course, when we balanced it, we had a 3 here and a 2 here. So again, in the lab, or your lab being home, you'd actually be doing this in units of grams. We might like to say something like this. What mass of NH3 could be made when we could say 57.4 grams of H2 react with an excess of N2. So what mass of NH3 can be made when 57.4 grams of H2 react with an excess of N2? So now if we remember, we go back to this equation. What do these coefficients stand for? What do these coefficients stand for? We don't write the 1, but if we did, we go right here. What do the coefficients stand for? Moles, right. So if we see a problem like this, which is given in grams, and we're looking for mass, which is also in units of grams, if we want to use this chemical equation, that means we're going to have to take the number of grams first here and convert it to moles. And once we convert the grams of H2 to moles of H2, we're trying to get over to NH3. So once we have moles of this stuff, then we need to convert from moles of H2 over to moles of NH3. Once we get our moles of NH3, then we can convert it over to grams of NH3. So let's go through the steps here. Again, we're given the 57.4 grams of H2, and we're looking for the mass of NH3. And what should we do with this piece of information right here, the fact that we have an excess of N2? What do we do with our wheels problem? We had an excess of wheels, or excess of frames and bumpers. We disregarded it, exactly. So when you look at the wording here, if we have an excess of something, it can be disregarded. It's not entered into the equation at all, or into our calculation. So we'd start with the 57.4 grams of H2. We're looking for the grams of NH3 out here in the answer. And we said now that our first step here, if we're going to convert from one substance to another, is we need to use the equation. We need to first take the number of grams here and convert it to moles. So to convert to moles, how do we convert grams of H2 into moles of H2? This is an exam 2 question. If we have 1 mole of H2, how many grams of H2 are there? How do we find that out? Do you remember? What are we going to need? We need our periodic tables out. Oh, let's get on the periodic tables. We need a new one. That one. All right, so if we want to figure out the number of grams of H2 and 1 mole of H2, here's H right here. How many grams of H2 are there in 1 mole of H2? Anyone? Anyone? Is it 1.008? Or is it 2.016? 2.016, right? Remember the formula here is H2, so we need 2 of the hydrogens. So there's 2.016 grams of H2 for every 1 mole of H2. And remember now that we had a name for this. This conversion that we're looking at right here is referred to as the molar mass. This is the molar mass. So that's not anything new. We've dealt with the molar mass before. Grams of H2 are going to cancel out. Now we have moles of H2. What can we convert moles of H2 over to? What would the next step be here? Any ideas? Got it there, Alina? NH3? Yeah, and which units of NH3? Moles or grams? Moles, right. And so how do we go from moles of one substance to moles of another? We use what's called the molar ratio, right? So the molar ratio, in this case, our molar ratio would relate moles of, see what's going to have to go on the bottom here, moles of H2, and on the top would be moles of NH3. Good. Help me out with the numbers. What number is going to go on the bottom? 3, and on the top would put in 2. And again, this is telling us that for every 3 moles of H2, we have 2 moles of NH3. And we call this one here a molar ratio. The molar ratio comes from the coefficients in the balanced chemical equation. And these cancel out. Now at this point, we have moles of NH3. We're trying to get over to grams of NH3. So how do we convert from moles over to grams? What do we need to do here? Go back to the periodic table and we find out the mass of 1 nitrogen and 3 hydrogens. So we could say for every 1 mole of NH3, 1 mole of NH3 is equal to how many grams of NH3? And what number should this be right here? How many grams? .03, right. And remember now that this conversion here is called a molar mass. This is not a new conversion. So now if we put this in here, what's going to go on the bottom? One mole of NH3. What's going to go on the top? 17.03 grams of NH3. At this point then, moles of NH3 are going to cancel out. Once they do, we run this through our calculator. 57.4. We divide it by 2.016, multiply by 2, divide it by 3, and multiply again by 17.03. Now I have an answer that looks like this. It's 323.2546, etc. How many significant figures should be in the calculated result? 3. So I'd round this off to be 323 grams of NH3. So this is what stoichiometry is all about. We call this type of problem a mass-to-mass problem. Mass-to-mass problem, we're starting with a mass, we're looking for a mass. This is one that involves these 3 conversions, a molar mass, a molar ratio, and a molar mass. And the only thing new that we really learned here today thus far is what is a molar ratio. And a molar ratio enables you to convert from one substance to another substance using a chemical equation. The other thing that a very common mistake students make in these is that, remember that molar mass is always the grams contained in 1 mole. This over here, number of grams contained in 1 mole. So when you look at the molar masses, don't pay any attention to the coefficients in here. The place where we take the coefficients into consideration is here in the molar ratio. Okay, let's try one more. Let's try this one here. Let's say we want to know what mass of H2, will react with 3.25 grams of N2. And to help us out, I'm going to rewrite our chemical equation in here. N2 gas reacts with H2 gas. Now you don't need to rewrite it. I'm just doing it because it scrolled off the screen. So I'll put this in right here. Okay, so we'd like to know what mass of H2 will react with 3.25 grams of N2. So let's start off with this one. We'll do this one a little quicker. What are we given? 3.25 grams of N2. What is it we're looking for in this problem? And the mass is going to be measured in units of grams. So we're coming out here, we're looking for grams of H2. So now let's follow our steps. This time I'm not going to write out the conversions down here. We'll just place them directly into the calculation itself. So on the bottom here we need grams of N2. On the top would put in 1 mole of N2. So now we need to figure out the number of grams in 1 mole. Come back to our periodic table. We see that nitrogen, one of them is 14.01. So that means that N2, 1 mole would have a mass of 8.02. Grams of N2 cancel out. Now we have moles of N2. We're trying to get over to grams of H2. In order to convert from one substance to another, we need to use a conversion called a molar ratio. So on the bottom here, we're going to put in moles of N2. On the top would put in moles of H2. The numbers we put in, on the top would put in 3, on the bottom would put in 1. Again, these numbers come from the coefficients in the balanced chemical equation. Units cancel out. And now we have moles of H2. We're trying to get units of grams of H2 in the answer. So on the bottom here, we're going to put in moles of H2. On the top would put in grams of H2. Remember now that the molar mass is always the number of grams in 1 mole. We already calculated this mass. 1 mole of H2 has a mass of 0.16. Go ahead and cancel out the moles of H2. And once we do this, we can then run this through the computation. We'll take 3.25. We'll multiply this by 3. And again by 2.016. We divide the result by 28.02. And how many significant figures should be in the answer? 3. So the 3 significant figures, we would write this as 0.701 right there. And that would be the result of this calculation. Any questions? This is still so weird, just before we go in here, but I'll get over it. All right, we'll look at one more. And the one more we're going to look at will be this reaction. We have potassium chlorate, solid, decomposes to yield potassium chloride, solid, and oxygen gas. And we'd like to know what mass of O2 would be produced. What mass of O2 would be produced by the reaction of 7.5 moles of KClO3. Now we need to pay close attention to the units here. And we should also look at our chemical equation and realize something's wrong with this chemical equation. And what's wrong with it? Not balanced. So let's go ahead and balance it. Looks like potassium and chlorine are already balanced, so we need to look at oxygens. We have 3 on the left, 2 on the right. That means in front of the KClO3 we need a 2. And in front of the O2 we need a 3. And because we put a 2 in front of the KClO3, what do we need right here? A 2 here as well. This thing now is a balanced chemical equation. Let's go ahead and start off this problem. We have 7.5 moles of KClO3. What are we looking for in this problem? Grams of O2. So now, in this case, we are given moles of KClO3, not the number of grams, but the number of moles. So what is going to be the first step we need to do with this problem? All right, now we're going to cancel out the moles of KClO3. Molar ratio, good. So this time we skip straight to the molar ratio. We're going to convert from one substance to another. We'll put moles of KClO3 on the bottom. On the top, we'd put in moles of O2. The number that goes on top is going to be 3. On the bottom, we'd put in 2. And of course, those come from the coefficients of the balanced chemical equation. And this is our molar ratio. Moles of KClO3 cancel out. Our next step is to convert moles of O2 over to grams of O2. Convert from moles over to grams. What do we need on the bottom? 1 mole of O2. What do we need on the top? 32, yep, 32 grams of O2. The conversion here is referred to as the molar mass. And we're only learning one new thing here thus far, that's the molar ratio. Moles of O2 cancel out. Once we do this, we take 7.5, we multiply it by 3 divided by 2, and multiply again by 32. We wind up with an answer of 360. Of course, by writing 360, we don't know how many significant figures this number has. How many significant figures should this answer have? 2. So what is the best format to write this answer in to show 2 significant figures? Scientific notation. So to write it in scientific notation, I write this answer as 3.6 times 10 to the second grams of O2. And that then would be the calculated result. So that's our first hour here. Any questions that you have on this stuff? All right, going into hour 2. Here's what we're going to do to start hour 2. We have these 3 questions right here pertaining to this particular equation. These 3 questions will show up in the Socratic map in order. I'll give you till about, we're going to work a break into here as well. So somewhere around 9:10, 9:15, we'll resume on this. So work in a break. Either take your break first and then work on it, or work on this, then take your break. So somewhere around 9:10, 9:15, we'll resume. And these 3 questions will be in order on the Socratic app coming up. Any questions? All right. And I'll put them up on the Socratic app. There we go. And you can monitor your score. And we'll put these back up here.